harmonic motion is sometimes called spring motion. You know, this picture shows if you have a spring with a weight attached to the end, you know, if you pull down the spring and then let go, it's going to bounce back and forth. And that movement can actually be modeled with a trig function. The place, you know, we have our 0 point, that's like your equilibrium position, and you'll go above and below that as it moves around.
No. I came from A+.
Okay. The equations that we're going to use, we're talking about this type of motion. It's either a sine or a cosine. How would you know if the equation were sine or cosine?
Where it starts.
Where it starts. If it starts at its equilibrium, then it would be a sine. But more often, if you're going to like cause the spring to move, you're going to have to stretch it beyond its equilibrium. So pretty much all of these we're going to look at today are cosines, because in order to start the movement, you have to move it beyond its equilibrium to start. With this, A and omega, that's just like the A and B we've been looking at. A representing the amplitude. Period, if it's a B, we call it 2 pi over B. Because we put an omega here, your period is just 2 pi over omega. The new thing that we have not talked about before, frequency is omega over 2 pi. Frequency is just the reciprocal of your period. So the period is how long it takes to complete an entire cycle. And the frequency is how many oscillations it would make in a given period of time. All right. So let's just look at an example. Suppose an object is attached to a coiled spring. It is pulled down a distance of 5 inches from its equilibrium position and then released. The time for one complete oscillation is 4 seconds. We're going to give an equation for it. Okay. So, my equation, I'm going to say S of t. If it starts, it was pulled down. So we have our equilibrium and we pulled it down to begin. So is that sine or cosine? Cosine. But cosine normally starts at its high point, so what would be in front of this? A negative. How far down did we pull it? 5. So that's like your amplitude. So it's a negative 5 cosine. And then we just have to find our angle here. Okay. We know that the time for one complete oscillation is 4 seconds. So what is 4 here? It's a period. So in terms of our equation, we always do 2 pi divided by the number in front of x, which in this case we're using omega, but you could put a b there, it doesn't matter. And that equals 4. So if I want to solve, that means 2 pi equals 4 omega divided by 4, so omega is pi over 2. So it's 5 cosine of pi over 2t. That is my equation. Does that make sense to everybody? Okay, what doesn't make sense?
How's it cosine when?
If it's sine, it would have to start at 0. So because you've stretched the spring to begin, it wasn't starting at its 0 point. So it had to have been cosine. Remember, cosine always starts at its high point because it started at its low point. That's why it was a negative. Cameron, do you understand why it was cosine? Okay, do you understand where we got the negative 5 from? Okay, so then you just had to find your angle. This 4 is your period. So find period by doing 2 pi divided by the coefficient of x. So 2 pi over omega equals 4. Part B, I want to know the position after 1.5 seconds. We're actually just going to use our calculators for this. Make sure you're in radian mode, please. So you are just finding s of 1.5. So negative 5 cosine of pi over 2 times 1.5. Just plugging that in for your time. gonna get, if I just go to a couple decimal places, about 3.54. My position, this was, we were measuring our distance in inches. So essentially what this is saying, I didn't ask you to explain, but your equilibrium is at 0. We started out 5 below that. Right now we're just above. Our spring has bounced up a distance of 3.54.
Would this mean so the way you're saying, like, if you pull this straight down, the spring's just going to go up and down. So are you saying, like, if the spring is moving?
We are ignoring the dampening effect that, over time it will oscillate less. We're kind of ignoring that right now. We're living in a very simplistic world and assuming it would just keep going. Okay.
I got a negative number.
Are you in radian mode?
Yeah. This is what I should be doing.
You didn't have pi.
Oh, I thought we didn't do pi.
With this, we're trying to get an overall decimal, so you want to include.
That should be nice. Thank you.
You're welcome. Anything else? Okay, last question. I want frequency. Frequency is just the reciprocal of the period. So my period was 4, so the frequency would be 1/4. That's oscillations per second. In other words, in 1 second, it's completed 1/4 of its total cycle. Questions there? I am actually not going to do example 2. We are going to go to this one next. So a weight on a spring has an initial position, S of 0. So at time 0, the height is 2 inches, and a period of 0.5 seconds. Part A, find a function, I can't talk, that models the displacement using this form. So what is my amplitude here? 2, right? We start out 2 above. Am I flipping this one? No, because it started out at its high point. P is my period, so we know the period is 0.5. So we have S of t equals 2 cosine. We just have to find this omega. So remember, period is 2 pi divided by omega, and that equals 0.5, or 1/2. So if I cross multiply, omega is 4 pi. So it's 2 cosine of 4 pi t. Part B, evaluate S of 1. So what do you have to do? Plug in a 1. And what do we get out? 2. That would be, that's a height, so it would be measured in inches. Okay, I want to know if it's moving upward, downward, or neither at that time. Okay. How you know? It might help you if you're struggling with that to just draw yourself an extremely basic graph. Okay, we are starting at time 0. The period, so the length of time until this thing repeats, is 1/2 second. So we started at a height of 2, and at a 1/2, we would be back up there, because that's our period. That's how long it took to repeat. So we know the cosine graph looks something like this. We wanted to go all the way to 1 second, so at 1 second we're back up here. So we could see, if I drew a better graph, you can probably see that better, but Right here, we're just at the top. It's just got done increasing and getting ready to decrease, so it's not really moving up or down right now. What if I asked you, when does this thing hit its lowest point? The first time it hits the lowest point. Well, -2 is the lowest point. When does that happen? After what length of time? We know by the time you get to a half, you've done the whole thing. So you would hit your lowest point halfway in there, so it would be after 1/4 second. If I said after a third of a second, is it going up or down? Down. We know this would be, oh, would it? This is a fourth. As a third.
Oh, it's bigger.
Third is bigger than a fourth, so you'd be going back up. So it'd be going up. So if you draw yourself just a really rough graph, you can answer a lot of those questions about is it up or down, when does this happen? Any questions there? Let's look at this one. A note on the piano has a frequency F equals 27.5. Suppose the maximum displacement is S of 0 equals 0.21. Write your equation. So at time 0, we started out with a height of 0.21. What is that? Amplitude. Would I need a negative? No, because I started out positive. So it's just a positive 0.21 cosine. All right, now I have to find my angle. We know that if you do 2 pi over omega, you get your period. I didn't give you the period. I gave you the frequency. How are frequency and period related? Reciprocals. So if my frequency is 27.5, my period is so omega would be 55 pi. So it's 0.21 cosine 55 pi t. Questions on these? So, a couple things. The homework is 5 questions. Question number 6 does tell you to draw a graph. You do not have to draw the graph. So on number 6, you don't have to graph that. I do want to go ahead and grade our homework real quick. It'll only take us a couple minutes, and then you'll still have some time to start these problems. So if you could get out yesterday's